Have you ever wondered how the world Earth rotates and revolves? Does the star, the sun itself, spins around Earth? Or does the world, the Earth spins and revolves around the Earth? Well, based on Nicolaus Copernicus, who created the heliocentric theory that the Earth spins and revolves around the sun. But before we head to theory, let us first know his early life and education. Nicolaus Copernicus. Nicolaus Copernicus, a Renaissance mathematician and astronomer, made a groundbreaking contribution to science with his heliocentric theory. In the early 16th century, Copernicus proposed a revolutionary concept that the Earth and other planets revolve around the Sun, challenging the prevailing geocentric model of the universe. This bold idea fundamentally reshaped our understanding of the cosmos and laid the foundation for modern astronomy. Early life and education. The original form of his name was Michael Copernic Polish, or Nicolaus Copernic, German. Nicolaus Copernicus is the Latin translation of his name, originally Nicolaus Copernicus with double P, but the Revolutionibus Rheticus, his sole pupil, published the name Nicolae Copernici. The surname Copernici was apparently given to the people from the village of Copernici. He was born in Torun or Torn, a city in northern central of Poland. And he was born on February 19, 1473 and died on May 24, 1543 at the age of 70 at Frequenberg in Poland. He was the youngest son of a wealthy merchant. His parents are Nicolaus Copernic, which is similar to his name, and his mother named Barbara Watson Road. When young Nicolaus was 10 years old, his father died. Lucas Watson Road guided Copernicus towards ecclesiastical studies. Copernicus' most important patron by far was his uncle Lucas Watson Road, who arranged for the canonry at Frauenberg and appointed Copernicus to a trusted position as his medical advisor for 6 years. This was also the time that his uncle Lucas Watson Road adopted the 4 siblings. Lucas Watson Road was a wealthy, powerful man in Warmia, a small province in northeast Poland under the rule of a prince-bishop. Is an important figure for a Nicolaus. He was the one who educated him at the University of Krakow. And also because of the influence of his uncle, Copernicus became a canon of church official, but he did not study the priesthood. And when he also returned to Warmia when Copernicus was 30 years old, Lucas hired Copernicus as his secretary and personal physician.
In his early education, Copernicus attended the Cathedral School of Nicolaus from 1488 to 1490. Having been sent there by his uncle, he received a good humanist education at this school. Some historians believe that he might have initially gone to St. John's School in Charon, where his uncle taught, and later he went to the Cathedral School in Nicolaus. This school aimed to prepare students for entry into the University of Krakow. During his time at the University of Krakow from 1491 to 1495, Copernicus studied mathematics and astronomy. The university was in the capital of Poland at the time. He, along with his brother Andres, enrolled in various subjects like Latin, mathematics, astronomy, geography, and philosophy. His knowledge of astronomy was influenced by Johannes de Sacrobosco's Tractatus de Spira. The curriculum included mathematical courses that introduced Aristotle and Ptolemy's views of the universe. Students learned to understand calendars, calculate holidays, and gain practical navigation skills. Additionally, They studied astrology, which involves calculating horoscopes based on birth times. After 4 years at Krakow, Copernicus returned to Rome without formally graduating, as this was common at the time. His uncle still aimed for him to have a career in the church, offering stability for his pursuit of knowledge. In 1496, Copernicus traveled to the University of Bologna in Italy to study canon law, a subject he was sent there to pursue. His stay in Bologna lasted from 1496 to 1500. During his time in Bologna, he studied canon law officially but also explored Greek, mathematics, and astronomy. Copernicus rented rooms from astronomy professor Domenico Maria da Novara and began to assist him with observation, which stimulated his interest in astronomy. While in Bologna, his uncle nominated him for the position of canon at Bridge Cathedral, which he received official notification of on October 20, 1497. This appointment provided him with a comfortable income without the obligation to perform any duties. In 1500, Copernicus visited Rome and stayed there for a year, where he lectured to scholars on mathematics and astronomy. In 1501, after a period in Rome, Copernicus returned to Bridge and officially became a canon. Since he hadn't completed his canon law degree in Bologna, he requested permission from his uncle to return to Italy. His proposal to study medicine was well received, and he received financial support from the cathedral chapter. He embarked on a journey to Padua, known for its renowned medical school. During his time to Padua, he studied both medicine and astronomy. Copernicus likely had another, undisclosed, reason to continue his astronomical studies during this time. In the spring of 1503, Copernicus made the decision to pursue his doctorate in canon law. Instead of returning to Bologna, he chose to earn his degree at the University of Ferrara. After successfully obtaining his doctorate, he spent a few months in Ferrara before heading back to Padua to continue his medical studies. It's worth noting that there is no record of him officially graduating from Padua.
In case you are not familiar with the duties of a canon, it refers to someone who oversees a cathedral or other churches known as collegate. After studying at the University of Ferrara, upon returning to his native land, he granted leave from his official duties and as a canon in the Ermelo chapter at Fuldenberg, meaning he was not necessarily overseeing cathedrals and other collegates. The Revolutionis Orbium Coelestium on the Revolution of the Celestial Spheres 1543. First major work on heliocentric theory, counter to the eccentricity Plometti model, helped guide the scientific revolution. Copernicus was not, in the fact, first person to conceive heliocentrism. The ancient Greek astronomer Astyages or Simon apparently proposed a theory during 3rd century BC. However, unlike Copernicus, Astyages failed to work out the details. The Revolutionibus is divided into 6 sections or books. 1. Heliocentric theory as the basis of his cosmology and ongoing calculation. 2. Trinomic tree to solve various motion or heavenly bodies in the sky. 3. Motion of Earth. 4. Motion of Moon. 5 and 6. Motion of the planets. Aristotle held that the planets are carried around the center of the universe embedded in unchangeable materials, invincible spheres and fixed distance. Ptolemy, he said that the Earth was center of the universe and was motionless. He believed all the other heavenly bodies moved in complicated patterns around the Earth. Solved their problems by postulating three mechanics uniformly revolving off-century circles called encetrics, epicycles, little circles, whose centuries move uniformly on circumference of circles of large radius, difference, and equants. Copernicus' primary reason for rejecting the Ptolemaic model of solar system that was it mathematically intelligent, also because he found it too contrived, reasoning that there had to be a simpler hypothesis which could explain everything to his satisfaction.
Little commentary, or other known in Latin, Commentarius. Sometime between 1508 and 1514, Copernicus wrote this short astronomical treatise which laid the basis for his heliocentric or sun-centered system. But he distributed this little book, not printed but handwritten, to a few of his friends who knew that he was the author, even though there was no author written on the title page. This was a groundbreaking departure from the prevailing geocentric model, which is made by Ptolemy, which held that the Earth was the center of the universe. In the treatise, he correctly postulated the order of the known planets, including Earth from the Sun, and estimated their orbital periods relatively accurately. This book actually contains only the outline of an early version of his revolutionary heliocentric theory, or his major work of the universe, and it consists of 7 axioms, which Copernicus gives, which he only believes based on the conclusion he made after observing and studying the universe. It is likely that he wrote the little commentary in 1514 and began writing his major work, De Revolutionibus, or On the Revolutions of the Heavenly Spheres, in the following years. Somewhere between the end of 1514 and beginning of 1515, he started working on his major work. It is equally clear that his fame as an astronomer was well known for when the Fifth Lateran Council decided to improve the calendar, which was known to be out of pace with the season. The Pope appealed to experts for advice in 1514. One of these experts was Copernicus. Copernicus' standing as respected astronomer and his involvement in providing expert advice on calendar reform during the early 16th century. Many experts went to Rome to advise the council, but Copernicus chose to respond by a letter. He did not wish to contribute more to the discussion of the calendar, since he felt that the motions of the heavenly bodies was still not understood with sufficient precision. This decision reflects Copernicus' commitment to precision and accuracy in his work as an astronomer. Copernicus believed that a deeper and more accurate understanding of the heavens was necessary before calendar reform could be effectively undertaken. Rheticus, whose full name was George Joachim Rheticus, was a significant figure in the dissemination and popularization of Copernicus' heliocentric theory. If not for Rheticus, Copernicus will not be convinced enough to publish his major work. His agreement with Copernicus' theory was based on the scientific merits of the model and its compatibility with the data and observation of the time. Rheticus' support and efforts to promote Copernicus' work were instruments in the eventual acceptance of the heliocentric model. In this book, Rheticus introduced and explained Copernicus' heliocentric theory. clarifying its concept and promote the idea to the scientific community. It played a crucial role in preparing the way for the eventual publication of Copernicus' De Revolutionibus. In 1538, Rheticus traveled to the Nuremberg where he met the painter Johannes Petrus, who presumably commissioned him to persuade Nicolaus Copernicus to publish his magnum opus or his major work in Nuremberg. At least Petrus gave him 3 books from his publishing house as a gift for Copernicus. Johannes Petrus. Johannes Petrus is also known as Johann Peter, was a German printer and publisher during the Renaissance. He is notable for his role in the publication of Nicolaus Copernicus' groundbreaking work. Rheticus left Frauenburg to return his teaching duties at Wittenberg. He took the manuscript with him in order to arrange for its publication at Nuremberg, the leading center of printing in Germany, which he chose the top printer in the city, Johannes Petrus, who had published a number of ancient and modern astrological works during the 1530s. However, Rheticus was unable to remain unsupervised. He turned the manuscript over to Andreas Osander, a theologian and being a pastor in position and a clergyman, experienced in shepherding mathematical books through production as well as a leading political figure in the city and ardent follower of the Luther. However, Oriandus added a preface suggesting that the model described in the book was not necessarily true or even probable, but was useful for computational purposes. In addition, he changed the title on the revolutions of the orbs of the world to Six Books Concerning the Revolutions of the Heavenly Orbs, which sparked debate and differing interpretations of Copernicus' intentions in the years to come. Ironically, Osander's letter made it possible for the book to be read as a new method of calculation, rather than a work of natural philosophy, and in so doing may even have aided in its initially positive reception. Some suggested he may have been trying to avoid potential religious controversy and criticism from the Catholic Church, as the heliocentric model challenged the geocentric views held at that time. His death. Toward the end of 1542, Copernicus suffered a cerebral hemorrhage followed by a partial paralysis, and took permanently to his bed. He is reputed to have awoken from stroke-induced coma, looked at his book, and died peacefully at the age of 70 in 1543. Legend has it said that a copy of the Revolutionibus, or his major work, was placed in Copernicus' hand a few days after he lost consciousness. However, this anecdote doesn't have enough support and proof as may have been embellished or added to the story over time to highlight the significance of his work and his dedication to his revolutionary ideas. While it's a compelling and memorable detail, it should be taken as a legend rather than confirmed historical fact. Publication of Copernicus' heliocentric theory in 1543 is a good beginning point for the scientific revolution. Throughout the West, modern science began to take shape in many ways. In the 17th century, the work of Kepler, Galileo, and Newton would build on heliocentric universe of Copernicus and produce the revolution. Kepler. A generation later, Kepler penned a work in defense of the Copernican model, but not on physical or mathematical grounds. Kepler's argument was religious. He said that since the Son of God was at the center of the Christian faith, the Son ought to be at the center of the universe. Galileo. He subsequently used his newly invented telescope to discover four of the moons circling Jupiter, to study Saturn, to observe the phases of Venus, and to study sunspots on the Sun. Galileo's observations strengthened his belief in Copernicus' theory that Earth and all planets revolve around the sun. Newton. Newton argued that gravity provided the reason why planets did not fly off into outer space, and inertia explained why they kept moving. Newton's theory of gravity and three laws of motion provided the final proof that Copernicus, Kepler, and Galileo were right.